I can see the faces now. You seem a little bit tired, but I promise to not overwhelm you with heavy word slides. My name is Mirali Seyedrezaei. I'm studying mineral and energy economics in Colorado School of Mines with Dr. Maxwell Brown. Today I will be presenting my work on projecting mineral demand and energy transitions. I use a scenario-based stock flow model to estimate how the needs for critical minerals will evolve under different IEA scenarios, including the STEP scenarios and net zero scenarios. In my work, I'm coupling these two scenarios with the Bloomberg EV scenario. As the motivation of working on this project and taking it as a full-time job for this summer, as all you know, clean energy technologies like solar panels, EVs, wind turbines are far more mineral intensive than fossil-based systems, often using 4 to 6 times more materials. As deployment scales up, demand for minerals like lithium, cobalt, and rare earth element is projected to grow in some scenarios more than 500%. But at the same time, the supply chain are highly concentrated. For example, China is controlling roughly 90% of the processing for some critical minerals. For lithium, almost 65%. DRC is producing 70% of the world's cobalt, raising concerns about the future bottlenecks. And another motivation not written in here, I worked on no mineral, no megawatt paper that I saw was cited by some of the speakers yesterday. I'm happy about it. The second work that we worked on it was compete or collaborate, a game theory model for lithium market. So working on this project, I was looking for the next mineral that I want to work on it and come up with an optimization program for it. So looking at the scenarios we have in here, the IEA STEP scenario is based on the current and announced policies that are in act. It leads to slower clean energy growth and modest mineral demand. STEP was first introduced by IEA in the World Energy Outlook in 2010. Within those years, it was first named a reference scenario. The second scenario, the net zero scenario, targets the 1.5 degree Celsius climate goal and results in much higher demand. It's a bit more aggressive scenario in comparison to the STEP scenario. The net zero emissions by 2050 was introduced in May 2021. And the third scenario, the Bloomberg EV outlook, meanwhile, focuses on aggressive battery and EV adaptation driven by market forces, making it particularly relevant for battery metals. To not make it very mathematically complex, here, to estimate the material needs, we start by calculating how much new capacity is added each year as gigawatts. This includes both new installations and the replacements of the older systems that have reached the end of their lifetime. Mathematically, we are taking the differences between the total capacity in year T and T-1 and adding any capacity that needs to be replaced. Having these new investments capacities in gigawatts, then we are bringing in the material intensity for each technology. That's the amount of each material needed for per gigawatt. So this gives us the total demand for each material year by year across all technologies. And in this work, we are considering all intensities constant over time and are based on the previous studies that has been done by mine students and Collins and Watari. So having a general look on the electricity capacities by each technology, here we compare the electricity generation capacity mix under the STEP scenario for 2020 and 2050. In 2020, fossil fuels dominate the system, making up to 54% of the total capacity, then followed by hydro and solar and wind, 10%. Other sources like nuclear, biomass, and waste play like smaller roles. But by 2050, total capacity grows more than threefold to, in here we have it 30,000 gigawatts, becoming the dominant, and we have like the dominant energy sources in here. In 2050, we have the solar system. The slides are, I think, a bit mixed. This is my first slide, but I revised it later. It's not in here, so I will try to work best on it. So we have the STEP scenario. In here, between the 2020 and 2050, we see the solar increases from 12% to 59%. Fossil fuels still are playing a role, around 15%, from the main 54% that we had it. Wind still is playing a role as 50% in the scenario, and in this scenario, we are requiring about 28,000 gigawatts of new capacities. So there are 33 minerals that I worked on it in this project, but some of them were interesting for me to check on them. In the figure on the right-hand side, you can see the aluminum, copper, and nickel. We have huge spikes on aluminum, which is mainly because we have higher gigawatt capacity needed for investments after 2023, and it's almost increases 300% to 400%, which spikes the need for the aluminum. But at the same time, minerals like manganese, lithium, and cobalt increase in the scenario. The previous slide was showing the total tonnage of the mineral that we were requiring, but in here we were trying to see how many ton of that mineral can be recycled in each scenario. In both figure 3 and 4, we can see that they are steadily increasing. The recycling is increasing, but at the same time, it's not still enough. So we need virgin materials to be mined at each year. So the second scenario, step scenario, new capacity that we need in this scenario follows almost the same path, but the step scenario is a bit exploratory and conservative scenario in comparison to the net zero scenario. Also in here, the spikes in the aluminum is because of the huge increases in the need for the new investments in electricity capacity in between especially years 2023, 2025. And then also the needs for other minerals like lithium, cobalt, and manganese increases. In both scenarios, you can see steadily the recycling for these minerals are increasing, but still, as I said in the previous slides, it's not enough. This is the slides comparing the requirements for the raw materials between 2020 and 2050 for all the 30 to 33 minerals that we checked in our studies. Generally, we see that between the two times, the requirement for the minerals are increasing. Demand for nearly all of the key minerals is expected to rise dramatically. For example, lithium demand is projected to increase by more than 1,500%, growing from around 5,400 tons in 2020 to over 90,000 tons in 2050. Similarly, cobalt demand grows by over 1,300%. These steep increases reflect their vital role in electric vehicle batteries and energy storages. Traditional metals also show large increases. Aluminum demand is projected to grow over 600%, reaching nearly 35 million tons. Copper, used across renewable infrastructure and electric vehicles, sees around more than like 400% increases. At the same time, we also observe significant growth in less discussed elements such as manganese, nickel, silicon, all of which more than double in demand. Even smaller volume elements like gallium, selenium, tellurium grow over sixfold. This data highlights how a clean energy transition is not just about reducing the fossil fuels, it's also about massively scaling up critical mineral supply chain without proactive investment in extraction, recycling, and substitution. Bottlenecks in mineral availability could become a major constraint on global decarbonization goals. Thank you so much.